Welcome guys back to the channel. In this video we will be proving irrational numbers when converted to decimals are non-terminating as well as non-recurring decimals. So let's begin. We'll take case 1. We'll prove it by contradiction. We'll assume that the irrational numbers we are seeing are some terminating decimals. There are some terminating decimals which are irrational numbers. So this is our first assumption. Now we'll look at how typically a terminating decimal looks. So for example, a terminating decimal is like 2.567965. This is an example of a terminating decimal where there is a integer before decimal and there is some decimal places after it. It is terminating because like it ends somewhere. It doesn't go on forever. So this is a characteristic of a terminating decimal. How we can write it as a fraction kind of thing is like just shifting the decimal places ahead, and like there are 6 decimal places, so just shifting decimal point here and dividing by that many 10 raised to power here. For example, in this there are 6 decimal places, so we shift 6 decimal places here and divide it by 10 raised to 6, and this is a rational number of a p by q form. And we can do this for any type of decimals, any type of terminating decimals, because like n decimal points are there after decimal places are there. We can just shift those n decimal places ahead, making it an integer, and divide it by 10 raised to n, which is a p by q format, which is a rational number. So terminating decimals are always a rational number. So our irrational number cannot be terminating decimal. So case 1 is disproved. Let's move ahead. Let's move to case 2. That recurring decimals are also rational numbers. This we have to prove. So we'll assume that they are irrational and then we'll contradict. So let's say take an example 0.7 bar. This can be written as 7 by 9. This is a rational number. How it goes is as follows. 9 zeros are 0 and then 7. So just add a decimal. Then 70. 9 sevens are 63. So 70 minus 63 is 7. Then again we add a 0. 70. 9 sevens is 63, we subtract 63 from this 70, 7 remains, again add a 0, then 9 sevens are 63, and this goes and then goes on. So this is a phenomenon how we can write a recurring decimal numbers with rational numbers. We take one more example, let's say 0.437 bar, means it's 0.437, 437, 437 repeating. So this is also a rational number. It can be written as 437 by 99. How it goes is basically, when we divide 999 by 437 and let's say add 0 also, then it will get divided by 4. So minus 3996, 374 will be the remainder. Then again we will divide it by 3, 2997. Then again we will divide it by 7. And then what happens? 437 comes remainder again. So this is going to repeat. 437, 437, 437. This is going to repeat. So this is what is happening. So this is a trick to convert a recurring decimal to a rational number, and that's why every recurring number can be converted into rational number. We'll take one more example for let's say 0.6278 bar, in which 62 is non-repeating after a decimal, but like 78 is repeating. So it is 0.6278787878 and so on. So this is also can be depicted as a rational number. How? Like this. We multiply it by 100 first. This is 62.78 bar divided by 100. Now we can separate it like 62 divided by 100 plus 78.78 bar divided by 100. And 0.78 bar, as we learned in the previous work, that like 0.78 bar is just 78 by 99. So this can be written as 62 by 100 plus 78 by 99 into 100. This is a rational number. This is a rational number. Adding it would also result into a rational number. So recurring decimal can also be written as rational number. So both recurring decimal and terminating decimals are always a rational number. So irrational number are none of those. Irrational number are something different. So that's the proof. Thank you.